Thank you so much for the invitation to speak. So today I'm sort of picking up where Matthew left off and talking about filling some of these gaps. So what are our research priorities to try to advance wearables in physical activity surveillance? So at this point in the meeting, we had made all these decisions, technical decisions about devices, and Fiona now asks the question, where are we now? What are some of the key research gaps? And then can we start to build a theoretic framework to inform not necessarily what method we select, but what's the process by which we decide to select a method that we're going to use? And that led to the creation of a working group that has set up some progress and some future plans that I'll cover throughout the talk. So the question, where are we now, is really, I think, the question that a number of people have already put in the chat. What algorithms should be applied to device data to try to estimate these three set core metrics of interest? Of note, all of the things we're going to talk about today can be applied to other metrics, things that we develop guidelines for in the future, such as 24-hour guidelines. But today we're focusing on these three core metrics that WHO set out. So we're all familiar with the fact that these devices measure movement signals. So here's an accelerometer tracing from pickleball and from taking a walk. And we have to somehow apply some sort of statistical algorithm to try to predict whether they're taking a step during that time, whether they're sedentary, or whether they're engaged in moderate to vigorous physical activity. The consensus in the room was that there's lots of good news out there. There's been significant recent advances in algorithm development for wrist-worn devices that have been driven by the release of biobank data from other large cohort studies, as well as significant advances in deep and machine learning algorithms that have been applied to these data. The general consensus, which Fiona echoed in her talk, is that the opportunity to put wearables into global surveillance efforts and the existing available algorithms represent a transformational step forward for our field. They're increasing accuracy for MVPA and sedentary time compared to questionnaires substantially, as well as enabling step counting, which is anticipated in future guidelines. The bad news is that different algorithms still produce wildly different point estimates of physical activity metrics, which impacts our understanding of disease health associations and ultimately global prevalence levels. There are no benchmark data sets available to evaluate and give a concrete answer to the question in a head-to-head comparison, which algorithm is the most accurate and should be adopted. To briefly illustrate some of the issues when I say that we're getting wildly different point estimates of MVPA, this chart on the left over here is data from NHANES, where two different cut points were applied to estimate MVPA. In blue is the 2020 cut point, and in red is the 760 cut point. So participants were quartiled into different groups. We see with the 2020 cut point, there is about a 60% reduction in mortality risk for that third quartile group at about 23 minutes a day of MVPA. With the 760 cut point, we see similar reduction for that third quartile of 60% reduction in mortality, but that's now at about 100 minutes per day. So that's a huge gap that we need to reconcile before being confident in what that dose-response relationship truly looks like. Watson and colleagues about 10 years ago looked at adherence to guidelines based on that NHANES hip-worn data, and they found that depending on which algorithm was selected, either 6 or 98% of the population was meeting current physical recommendations. So clearly this has large implications for WHO surveillance efforts, setting global targets, all of the stuff that Fiona outlined in her talk. We're seeing a similar story emerge for sedentary time and step counts based on UK biobank data. So again, these are the same people. We're just applying different algorithms to the data. This section here in red, these are two different thresholds for quantifying sedentary time. So with a threshold of 25, that zone between 10 and 12 sedentary hours per day is where risk starts to increase. But if we select a different cut point, that's actually the referent level, and risk doesn't start to increase up till about 13 hours per day. Finally, with step counts, there's been two recent studies that have shown about a 40% reduction in mortality risk at either 6,200 or 9,200 steps per day. And these are, again, the same data sets, just the choice of different algorithms. So this is something that we need to do a better job of reconciling before we can make clear guidance on what algorithms should be selected. So the three kind of key research gaps related to evaluation were this need for rigorous independent evaluation of available algorithms, to carry that forward into a performance evaluation of algorithms in low and middle income countries, and then additional evaluations needed among older adults and mobility limitations. Today, I'm really going to focus on gap one, but I think it sort of sets the stage for moving forward into gaps two and three, and Marla will talk more about the older adults in a few minutes. So we need a rigorous evaluation. The question is, what is a rigorous evaluation? What is that level of evidence that we need before we can comfortably say this is an algorithm that can, or this is the or an algorithm that should be used in surveillance efforts? We know that surveillance data is going to be collected in real world conditions for 7 days in a diverse sample of participants. And so ideally, we would have an available benchmark data set that had device data collected in real world conditions, and then have an acceptable reference measure for each of the metrics we're interested in, to which we could compare the various device algorithms and evaluate them simultaneously. Unfortunately, we were unaware of such a data set that currently exists. And so we started to think about what we could do in the meantime before trying to build such a data set, or whether there was things we could quickly do with already collected data. And so that led to this formation of a working group, which we call WAVES. There's Algorithm Verification, Evaluation, and Surveillance Group. And our goal really is to try to incorporate a theory-based framework to inform the approach and data sets that should be included in this analysis, so that we have a rigorous framework that we can, and protocols, so that we can include good data, evaluate the algorithms, and make an informed decision. So really trying to standardize the process rather than at this point saying this is the algorithm we should use. So we drew on a framework that we had published a few years ago with a few adaptations. So this is a phased-based framework for evaluating and developing wearable algorithms. It ranges from phase 0, which is the reliability testing, so actually looking at the reliability of the device signal in something like a mechanical shaker, all the way up through phase 4, which is adoption. So do we have reproducible code and software available to implement that algorithm into an actual applied study, like a surveillance system or an intervention? These phases are meant to be iterative. They can go back and forth. But I'm going to focus in on these three phases in the middle, which are the most relevant to the algorithm selection because they're focused on the development and testing of algorithms. So phase 1 is we call development, which is a laboratory-based calibration where we have fixed start and end times and the activities are known. So you walk and run on a treadmill, complete 5 different activities for a set period of time. Phase 2 is preliminary testing, which can include semi-structured protocols and or some combination of real world for calibration. The key here is that in both phase 1 and 2, we're focused on methods development and calibration. So we're trying to build an algorithm and do some preliminary evaluation of that algorithm. The vast majority of studies in our field fall within this categorization. Excellent work by Marco Girgiu and the Wearables Landscape Group has comprehensively reviewed all of the development and validation studies that are out there. Many studies fall into this bin where we're trying to develop some sort of new algorithm, but unfortunately, their reviews found that many of them were of alarmingly low quality. Very few of these algorithms are ever tested in a different sample from the one in which they're developed. And so we really wanted to emphasize this idea of the phase 3 or the performance evaluation phase, where we're trying to independently evaluate the performance of the algorithm within real world conditions and compared to strong reference measures. So this is a critical step in our field, and we viewed, this is the type of study that we need in order to make that informed decision about algorithm selection. But unfortunately, it's rarely done, and the studies that are available tend to have really small samples. So if we take this plot here, we now have this phase 1, phase 2, phase 3, and on the x-axis here we have how representative those protocols are of the real world setting in which we're going to collect data for surveillance efforts. The next question became, in addition to just considering setting, what other characteristics of the studies and the protocols are needed to ensure that this is a robust performance evaluation? And the additional dimension that we wanted to really do a better job and a more thoughtful job of thinking about was what are the reference measures to which we're comparing the device algorithms. So now I've added this y-axis where we have reference measure quality from low to high. Obviously, as with most things, there's a continuum of these. We don't have these nice, neat phases and bins typically, but just for illustrative purposes, we've now sort of mapped these two considerations of the protocol that we think are really important to consider. So we want to have high quality reference measures, but we wanted to be more systematic about what we defined as a high quality reference measure. And so we looked to statements made by groups such as the InterLive Network, as well as in other fields. There's a joint committee guide for metrology, which is the study of measurement science. And they set thresholds and targets by which we can establish reference measures that are traceable to a primary reference measure method. So if we have a gold standard or a ground truth, and that may or may not be suitable for use in a real world environment, one example would be a direct calorimeter for measuring total energy expenditure. We know that we have doubly labeled water, which can be used in a free living environment and has a target accuracy within about 5% compared to direct calorimetry. So we're trying to establish this traceability chain between the different types of reference measures and be able to state which ones are high quality and should be used in this sort of performance evaluation. The traceability to the primary reference measure would be reference measures that are not that have not been shown to be accurate within 5%. So if we look at the example of step counts, so if we start to think about the protocols we have available and what types of studies we want to include in a pooled analysis of existing algorithms, we can map our different study protocols along these two metrics. So if we have a protocol where people are walking and running on a treadmill, that is low representativeness in terms of what the real world looks like. And then if our reference measure is another device, but not one that's traceable, so it's a Fitbit or something else that measures step counts, that's a low quality reference measure. If we think about a protocol where we have 3 hours of video recordings of people out in their natural environment, and then we've hand counted and labeled those steps, that is considered a primary reference measure. So that comes up here in this upper right-hand quadrant. We can plot different types of protocols. So a 7-day free living protocol compared to another device that's not traceable would fall over here. A semi-structured protocol with a series of different activities and hand-counted steps falls in here. And then if we had 7 days of data with an ankle-worn device, such as the stepwatch, we place up here in this upper right quadrant. The reason is that there's data to support compared to a primary reference, the ankle-worn device stepwatch has average percentage error of 4 to 5%. So suggesting it meets that criteria for traceability and is something that can be used in phase 3 studies. So I don't want to get too distracted by the relative value of all the different types of protocols out there, but I think that's something really important for our field to consider. There certainly is value in each of these types of studies along the way. But for this particular analysis, we know we don't want to be doing low representative, low quality studies. And we really want to be focusing in on having, looking at comprehensively at studies that are high representativeness of the real world and have good quality reference measures. Other key characteristics that we wanted to be included were that the sample is independent from the one in which the algorithm was developed, that these statistical analyses were appropriate and consistently implemented across different studies, and that we had a large and diverse sample. And we quickly realized that in order to achieve both the pooled analysis and a large sample was going to require merging different data sets. So the specific steps that we're trying to take in order to address these gaps are to empirically identify traceable reference measures for each of those core metrics, then identify available open source algorithms that are being used in applied studies and or have been recently developed and have strong evaluation results. They need to be open source and available for others to use. We then want to find data sets that have appropriate reference measures and simultaneous wrist-worn device data, and then determine the state of the field through a pooled analysis with existing data sets and algorithms. So we set it up as though we have study eligibility criteria. So we wanted raw wrist-worn device data that meets all the specifications that Matthew outlined previously, a traceable reference measure, and then data that were collected in a real-world or free-living setting. We categorize the two different types of studies that we want to include as first, those that have video recorded with a third-person view direct observation. They have a codebook available to reconcile operational definitions and record data for at least an hour. The second type of study that we want to include has 24 hours and ideally 7 days of real-world data collection with the wrist-worn device, but then with a traceable field-based reference measure. So for step counting, that's the ankle-worn device. For sedentary time, thigh-worn device, for example, ActivePal or other algorithms have been developed for thighs, worn devices for sedentary time. Moderate to vigorous physical activity, interestingly, is the one we've had guidelines for the longest, but was the least clear on what is a traceable reference measure. We've landed on a combined heart rate and movement sensor, which has been shown to be within about 5% compared to doubly labeled water. So in terms of where we are and what is coming next, we've identified data sets for pilot testing. We've developed a pipeline for implementing a series of algorithms. In progress right now is code review of that pipeline on pilot data sets, and then reconciling the ground truth across sites just to make sure that it's consistent. And then future plans are to open it up and incorporate more data sets for those who are interested and conduct independent statistical analyses. To give a little bit more detail here, for study one, the video recorded direct observation, we have 3 data sets currently with about 100 people and about 750 hours of recordings. We had already done some work harmonizing labels across those groups. So that's the pilot data we're going to be using. For study 2, we have a few data sets, but are definitely looking for more. We've identified and agreed on about 5 to 10 algorithms per metric. And then we're currently in the process of testing and ensuring version control and ensuring the pipeline works across different types of devices like Genia Active, ActivePal, Activity, etc. We're anticipated that we'll have the pilot analysis done in the end of the calendar year, and then moving on to Q1 of 2026, we'll be looking to incorporate more data sets. So for those who may have data that they may want to contribute to this effort, we anticipate distributing an interest form in the first quarter of 2026 through ISMPB, and are looking for studies with data that meet that criteria, particularly field-based measures of step counting and moderate to vigorous activity, and then sites that are willing to reprocess device data with the algorithm pipeline, and then able to share that process data for an external pooled analysis that will be led independently. And then finally, I just want to wrap up and start to think about, as people have mentioned, different metrics that might be of interest, different studies, different ways. I think that some of these efforts can inform hopefully broader progress in the field. So I'm going to walk through this figure. So we have a legend where we have a bullseye here that represents the target behavioral metric measured in the real world using an established reference measure. So the yellow bullseye here represents our truth. This is the true value in the population for that metric of interest. Each of these different darts represent some sort of different algorithm for a different behavioral metric. And then I'm going to show a series of single colored dartboards that represent different procedures for the algorithm development or calibration. So did you do a lab-based study that had 5 different walking and running activities or 15 different household activities? What was the reference measure of choice? All of these things represent different dartboards, and so the bullseyes are slightly different. So in terms of where are we now? We have a lot of inconsistently defined behavioral metrics. I think there's at least 9 published definitions for a step count, for example. And we see that we have a variety of different procedures that are not standardized, which results to different studies aiming at different targets. So I think each study is essentially developing and calibrating algorithms and aiming at their own target. And then many of these targets do not reflect real world truth for a given behavioral metric. So when we go to test these algorithms in a true phase 3 study where we have a value that represents the truth for that metric of interest, we're seeing many of our algorithms are non-comparable and inaccurate. So in terms of where we should go, I think establishing consensus operational definitions for those behavioral metrics and traceable reference standard procedures would mean that different research groups would implement traceable procedures for their development and calibration that would result in accurate estimates of that behavior that more reflect real world settings. And so then when we can conduct a large pooled benchmarking type analysis and provide such data, we should see commutability in our algorithms, which means that algorithms from different devices, wear locations, sites, lab groups should begin to produce more comparable results. And ideally, that algorithm accuracy and comparability will improve. So I'm going to wrap up there. I want to thank Fiona for really leading these efforts, Chuck Matthews, who's talked a lot about me with all of these issues and has been a longtime collaborator in thinking about these, the members of the WAVES working group, as well as our staff and students here, and ISMPB for hosting the webinar. Thank you.